Okay, so from this video, we will be starting with the uninformed search techniques. So in this video, we will learn our first uninformed search algorithm, which is BFS, that is breadth first search. And we will not only just learn and understand the algorithm, but also we will be implementing it in Python. And I will also try run and explain the whole process so it gets straight into your mind. So before directly jumping to the BFS algorithm, I would like to tell you about what exactly uninformed searches are. So imagine yourself standing at the starting point of the maze, that is you are here at the initial state, and your goal is to make your way out of the maze, that is reach the exit point of the maze. But the thing here is you have no map of the maze, and also you have no clue where to go, and you have no idea where the exit is. So now what can you do? What can you possibly do? The only way left to escape is now to discover all the paths one by one, hoping that eventually you will get your goal position. That is, eventually you will find the path where the exit is. And that's exactly how uninformed searches work in artificial intelligence. So uninformed searches are basically, you can say the algorithm has no extra knowledge about the problem. That is, the algorithm does not know where the goal state is or how to reach the goal state. You possibly just know is that you know where you have started, that is, you know the initial point, and you know how to move forward. That is, you know that, okay, these are my possible paths, and I have to that check in the path that whether the goal set lie in this or not, and you know how to recognize the goal state. That is, you at every path you will check that whether I have reached the goal state or not. But the important thing is that you don't know how far or close the goal state is from you until you find it. So this was all about the uninformed search. The important points to remember is that the algorithm does not know where the goal state exists, and it does not know how to reach that goal state. The only thing your algorithm knows is to discover all the possible paths. That is, now if I'm standing here, I have three paths in front of me. So now my task is to discover each path and check whether in that path my goal state lies or not. So that's what we have to do. We have to discover all the paths one by one, check whether the goal state lies there or not, and move forward. If the if the goal state is there, we will end the program and return the path. And if the goal state is not there, we will discover more and more paths. So this was all about the uninformed search. So now let's straight jump into the BFS algorithm. But before that, I would like to give a small suggestion that when I am explaining the algorithm, don't think about the code at that time. How will I implement the code or how am I going to write the code? Just understand the intuition I will be teaching and try to understand it rather than thinking about the code at that time. So yeah, now let's jump directly into the BFS. So, as we have already discussed before, BFS is an uninformed search algorithm, and we know that in an uninformed search algorithm, we know the starting position and we know what are the possible paths, and in that path, we have to travel and check whether the goal node is available or not. But what we don't know is where the goal state is and how to reach the goal state. So what we do is we keep exploring all the paths till we reach our goal node. And once the goal node is found, we return that path. So I will do is I will explore all the paths or node in this video. And at the end of this video, I will give you guys a goal node, and your task will be to find the goal node. And I'm 100% sure that you will be able to do it. Okay, so now what I have done is here I have taken a tree for easy understanding of the algorithm. And next I will also be explaining using graph that how the algorithm will work. So let's begin. So what we will do is we will take a node as a source node. You can take any node as a source node. There is no such any restriction. So if I take node A as a source node, so what BFS algorithm states is that we have to explore all the nearest neighbor first before going deeper into the search space. Listen again, very important. BFS algorithm states that we have to explore all the nearest neighbors first before going deeper into the search space. So if we consider node A, what we will do is we will first find out its nearest neighbors. So for node A, its nearest neighbors will be PQR. So now before going deeper into the search space, what we will do is in a path, we will store all its nearest neighbors. So we know we started with node A, So I will write node A first. Now we will write the nodes which we explored. So we explored its nearest neighbors. So we will write P, then we explored Q, then we explored R. So now what we will do is, after exploring the neighbors, we will explore the neighbors of those neighbors. So if we consider this node P, so neighbors for node P are B and C. So what we will do is, in path, we will add those neighbors. So I will add B and then I will add C also. So now again, before going deeper into the search space, and of course the search space end here, but again, if it had more nodes, we would have not gone deeper into the search space. We would have now gone to the neighbors of node Q. So for node Q, the neighbor is node D. So in that path, we will append node D also. So again, before going into the deeper into the search space, we will search for the nearest neighbors of node R. So for node R, the nearest neighbor are E and F. So in the path, we will add E and F. And that's it. We have discovered all the nodes of the search space. And if we consider this node D as our goal node, so what we will do is, once we find the D node, we will just return that path. We will just return. So what will we return? We will just return till node D. So we will just return this path, and that's it. It is as simple as that. So what we understand by this algorithm is that BFS works level by level. So what we did was, we were given this node A as our current node, the starting node. And what we did is, we explored its neighbors first. So we explored the nodes P, Q, R. Then again, we explored the neighbors of those neighbors. So we explored this level B, C, D, and F. And we will keep doing this. We will keep exploring level by level till we reach our goal node. And once we reach our goal node, we return that path. So what we did is, we traveled level by level. So I have represented it using these arrows. So we traveled in breadth direction, and that's why we call it as breadth first search. So now let us see how this will work on a graph. So with the help of this graph, I will explain the BFS algorithm, and at the end, it will be very clear in your mind. So as we know that we can take any node in the graph as our start node, there is no such any restriction. So if I consider this node A as our start node, I will create a path and write the node A in it. So in BFS, what we do is, we will first explore the nearest neighbors. So what are the nearest neighbors for node A? So the nearest neighbor will be node S. So we will write that in our path. So now what to do next? So have we explored the nearest neighbor of node A? Yes, we have. There is only one neighbor, that is node S. So what we will do is, we will now move to the next level, as we have already explored the neighbors of node A. So now what are the neighbors for node S? So they are Q and P. Then we will again append that in our path. So we will append Q and then we will append P. So now, have we explored all the neighbors of node S? We will say yes, P and Q we have explored. So now let's move to the next level. So what will be the next level? So we will again explore the neighbors for node Q. So what are the neighbors for node Q? You will say S, R, and T. But as you know, we have already explored the node S, so we will not be writing that in our path again. So the next neighbor for node Q is R. So we will append R in it, in our path, and the next neighbor is T. We will also add that node to our path. So now, have we explored all the nearest neighbors of node Q? You will say yes. So now, will we move to the next level? The answer will be no, because still the neighbors of node P are unexplored. So if we consider node P, the neighbors for node P will be S and R, but we will not be writing them in the path because we have already considered them in the path. So now we have license to move to the next level, as all the neighbors of node Q and P are explored. So now we will move to the next level, that is R. So we will consider this node R and see the neighbors for it. So the neighbors for R are P and Q, which are already explored in the path. So we will be not considering them. And the next node we will check the neighbors for will be T. So if we consider node T, the neighbors for node T will be Q and B. So as we know, we have already explored the node Q, so we will be not writing it in the path. So now we will check for node B. As we know that node B is still not in our path, so we will append it. And that's it. This is our path, and this is how we will explore using breadth first search. So I hope the algorithm is very clear in your mind. So now let's understand how the process of this algorithm will be and what data structures we will be using, what concepts we will be using. Let's find out. So for implementing BFS, we will be using a queue. So now if you don't know what is queue or don't know how to implement queue using data structure in Python, I have already explained those concepts in my previous video. You can just check the link in the description. Okay, so for implementing BFS, we will use queue, and we will also be taking two arrays, which will be path, and another array will be a visited list. So now we know that our source node is node A. So what we will do is we will take this source node. I will take this source node and put it in the queue. So I have taken the source node, and what I did is I pushed it in the queue. And the moment I pushed it in the queue, I will also append that node in path and visited list. So I will take this node A and also put it in path and in visited list. Okay. Okay, so very clear up to this point. So now here comes the main important part of this process. So now listen carefully. What I will do is I will pop the front element of the queue. I will pop the front element of the queue and push in the queue the nearest neighbors of that node, of the node which we popped out. So I will pop this node A from the queue, and I will push the nearest neighbors of that node A. So for node A, the nearest neighbor is S. So what I will do is I will take this S and I will push it in the queue after popping A out. And at the same time, what I will do is I will also append that node in the path and in the visited list. So I will take this and add it in the path, and at the same time I will add it in the visited list. And now what I will do is I will again repeat the process. So at the front we have S, so we will pop the front element out. We will pop this one out and append the nearest neighbors of that node in the queue. So the nearest neighbors for node S will be Q. This is Q, by the way. This is Q. So we will append in the queue, Q and P. So I will take this Q and push it in the queue. And also the P node is also nearest to S. So I will also append it in the queue. And as we know, when we append in the queue, we will also push it in path and visited list. So I will also add it in the path. And I will also add it in the visited list. So same goes for P. We will take P and push it in the path, and at the same time we will push it in the visited list. Okay, so now what we will do is we will again repeat the same process. We will pop the front element of Q, which is Q, and append the nearest neighbors of Q. So in this case, the nearest neighbors of Q will be S, R, and T. But will we take S and again push it in the queue? The answer will be no, because in the visited list we already have S. So now before pushing anything into the queue, we will check that whether this node is present in the visited list or not. If it is present in the visited list, we will not push that node in the queue. So if we try to push this node S in the queue, we will not be able to do so because it is already present in the visited list. So now we will move to our next neighbor, which is R in this case. So now will we push R in the queue? The answer will be yes, because in the visited list, there is no such node as R. So what we will do is we will take R and push it in the queue. And again, check if there are any other nearest neighbors. So yes, we have one more nearest neighbor, which is T. We will take this T and push it in the queue. And again, we know Once we push it in the queue, we also have to append it in our path and visited list. So we will take R and append it in the path, and at the same time append it in the visited list. Again, we will do same for T in the path and also in the visited list. So again, moving forward, we will repeat the same process. We will pop the front element of the queue, which is P, and look for its nearest neighbors. So for the nearest neighbors of P will be S and R, but it is already present in the visited list, so we will not push it in the queue. So this will be popped out without pushing its nearest neighbors in the queue. So again, repeat the same process. The front element of the queue will be popped. R will be popped in this case, and we will check for the nearest neighbors of the R, which are Q and P, which we will again not be appending in the queue because it is already present in the visited list. So again, we will repeat. We will pop the front element of the queue, which will be T, and look for its nearest neighbors. So nearest neighbors for T are Q and B. So for Q, we will be not pushing it in the queue, and for B, yes, we will be pushing it because it is not present in the visited list. So I will take this and push it in the queue. And at the same time, as we have pushed it in the queue, we will also append it in the path and also add it in the visited list. So again, repeat the process. Push the front element, pop the front element of the queue, look for its nearest neighbors. So the nearest neighbor for node B in this case is T. But again, we will not be pushing T in the queue because it is already present in the visited list. And that's it. Our queue is empty. We will stop the program and return the path. And this is what we got. This is the path which we got. And if we compare to what we discussed earlier, so we discussed this path and these both are same. Okay, so now let's move forward and write the code for this algorithm. So we are given with the adjacency list in the form of dictionary, which is representing a graph. And if you don't know how we represented the graph using dictionary, or if you don't know how to create an adjacency list or an adjacency matrix, I have already made a video on the basics of the graph, which we will be requiring for AI algorithms. So please do watch that before directly jumping to the code. So I have taken the same graph, which we discussed earlier. So now what I will do is from collections, I will import deck. So if you don't know what is deck, I have already covered it in my previous video. We use deck to implement stack or queue in Python. And now I will create a function BFS in which I will be passing graph and source node as the parameters. So now our first task was to push the source node in the queue. So first I will create a queue using deck data structure. And I will push the source node in the queue. So in the queue, I will push source node. And as long as we push something in the queue, we know that we also have to append it in our path and in the visited list. So quickly, I will create a path array and a visited array and push the source node in path and also in the visited list. Okay. So very clear up to this point. So now what I will do is I will run a loop till we have at least one element in the queue. So for that, while length of queue is greater than 0. So once the queue is empty, the loop will stop and the path will be returned. So now here comes the important part of the process. So what we do is we pop out the front element from the queue. So we will pop the front element using pop left method in deck and store it in the variable called front. And once we pop the front element, what we do is we push in the queue the nearest neighbors of that popped element. So for that, I will run a for loop for neighbor in graph of front. And if you are not understanding, don't worry, I will be dry running at the end, so it will get very clear in your mind. And once and if we have to append anything in the queue, we know that we have to check whether if it is present in the visited list or not. If it is present in the visited list, we do not push the element in the queue, and if it is not present, we will push it in the queue. So we will check if neighbor is not in visited, sorry, neighbor not in visited. So if the neighbor is not in visited, we will push that neighbor in the queue. So we will append it in the queue. So we know once we append anything into the queue, we also have to push it in the path and in the visited list. So I will also push it in the path, in our path, and also append it in the visited list. So that's what we do. And at the last, when the queue will be empty, the loop will stop and we will return the path. And that's it. So now what I will do is in the main function, I will call the BFS function and pass graph and source node as A as its argument. And if I print the function and run it, I will get this path. And if we compare to what we discussed previously, so this was the path which we got previously, and this is the output which we got. So these both are same. That means our BFS program was correct. And that's how we implement breadth first search algorithm in Python. So now let's quickly try run this algorithm. So at first what we did was we created a queue, and we in the queue we pushed the source node. So let's do that. So this is our queue. We will push the source node, which is A, in the queue. So we will push this in the queue. And what we did next was we created a path and a visited list. So we have already created a path and a visited list here. And we pushed the source node in both the path and visited. So let's do that. We will push the node A in path and also push it in the visited list. So next what we did was we ran a while loop till we at least have one element in the queue. So this loop will run till the queue contains at least one element. And next we did was we popped the first element out of the queue. So now let's pop the first element. So the first element here is A. So we will pop A out. So now after popping the first element, what we will do is we will run a for loop for the neighbors of that popped element. So for neighbors in graph of front. So this graph of front will give us the list of the neighbors. So in this case, our front element which is popped was A. So graph of front will give us this list which will contain S as its neighbor. So again, we will check this if statement will check that if the neighbor is in visited list or not. So let's check if it is in visited list. No, S is not in the visited list. So we will append it in the queue. So let's append it in the queue. And we know that once we append it in the queue, we also have to append it in the path and in the visited list. So let's do that. Append it in the path and also append it in the visited list. Okay. So now the for loop will end and second iteration will not take place because A has only one neighbor. So now this for loop will break and let's go to the while loop. So now will while loop run? So yes, it will run because our queue is not empty. As you can see, our queue has one element S in it. So the loop will not end. And again, we will pop the front element in the queue. So we will pop S. We will pop out S. And as we know, once we pop out S, we will check for its neighbor. So what are the neighbors of S? We will get this list and one by one we will iterate. So for the first iteration, our neighbor will be A. So let's check if the neighbor is in visited list or not. So first neighbor is A. Let's check if A is in the visited list. So A is in the visited list. So this loop, this if statement will not run and the first iteration will be complete. And now let's go for the second iteration for which our neighbor will be Q. So let's check if the Q is in visited list or not. So the Q is not present in the visited list. So what we will do is we will append Q in the queue. So we will take this queue and append it in the queue. And we know if we append it in the queue, we also have to append it in the path and in the visited list. So let's do that in the path, and it also goes in the visited list. Okay. So our second iteration is also completed. We pushed it in the queue. We also pushed it in the path and in the visited list. So now let's check for the third iteration. So for the third iteration, our neighbor will be P. So let's check if it is in the visited list or not. So P is not in the visited list. So we will push it in the queue. We'll push P in the queue, and at the same time we will push it in the path and also in the visited list. So all the neighbors of node S are completed. So this for loop will break and we will again go to the while loop. So while loop will check that if the length of Q is greater than 0 or not. So let's check. Yes, the length of Q is greater than 0. So this while loop will run, and again we will pop the front element of the queue. So this time Q will get popped, and now we will search for the neighbors of Q. So the neighbors of Q are S, R, and T. So for first iteration, our neighbor will be S. So let's check if it is in visited list or not. Yes, it is in visited list. So nothing will happen in the first iteration. So now for second iteration, our neighbor is R. So let's check if it is in visited list or not. No, it is not in visited list. So what we will do is we will append it in the queue, and at the same time in the path and in the visited list. Goes in the path and also goes in the visited list. Okay. So now let's check. The second iteration will be over, and third iteration our neighbor will be T. So now let's check for T if it is present in visited list. So no, it is not present. So what we will do is we will take T and put it in the queue. Okay. And as we have put it in the queue, we will also append it in the path and in the visited list. We explored all the neighbors of node Q. So the for loop will break, and again we will go to while loop and check if the length of Q is greater than 0. So the length of Q is indeed greater than 0. So the while loop will sustain, and again we will pop the front element out. So we will pop out P and check for its neighbor. So the neighbors of P are S and R. So for the first iteration, our neighbor will be S. Let's check if it is in visited list. So yes, S is in the visited list. So nothing will happen. Then again we will check for R. R is in the visited list. Nothing will happen. The for loop will end as we have explored all the neighbors. Now again it will check for while loop that if the length of Q is greater than 0. So yes, it is greater than 0. The front element of the queue will be popped, and then we will check for its neighbor. So we will check for the neighbors of R, which are Q and P. So let's check for the first iteration if Q is present in the visited list or not. So yes, it is present. Nothing will happen. Let's check for P. So P is also present. Nothing will happen. The for loop will break. Again, we will go to while loop and check if the length of Q is greater than 0. So yes, the Q length is greater than 0. So the loop will sustain, and we will pop the front element. We will pop T and check for its neighbor. So T has Q and B. So let's check if for the first iteration, our neighbor will be Q. So let's check if it is in visited list or not. Yes, it is. So nothing will happen. Let's check for B. No, B is not in the visited list. So let's take B and push it in the queue. Take this B and push it in our queue. At the same time, we will push it in the path and also push it in the visited list. Okay. So the loop will break, for loop will break, and again we will go to while loop and check if the length of queue is greater than 0. So yes, it is greater than 0. So now let's pop out the front element and check for its neighbors. The neighbor is T. Let's check if it is present in the visited list. Yes, it is present. So nothing will happen. This loop will break. So now when we go to the while loop, we will check if the length of queue is greater than 0. And we will see that the length of queue is now 0. That is now the queue is empty. So what will happen is the while loop will break, and at last we will return the path. And that's how we explore all the paths or all the nodes in the search space using breadth first search. So now, as I told you, that I will be giving you guys an exercise. So your exercise will be to find the goal node, which will be R in this case. And once you find the goal node, you will stop the loop and return that path. So your output will look like this was our path initially. So your output must look like this. That's it. It should be only up to R. And once you reach the goal node, you should stop the loop and return the path. And in the next video, I will also be providing the solution for this. I know this video might be a bit too long, but I have covered all the required things that you need to know about this algorithm. I have covered the theory part of this algorithm. I have explained the algorithm. Then we wrote the code of BFS in Python, and then we did a dry run and explained the whole code again. So this was a complete in-depth video on breadth first search algorithm. So in the next video, I will give the solution for the exercise, and I will also give a very optimal solution for it. So that's it for this video. See you in the next video.